In this video, we're going to do some extra problems that involve planes in three-dimensional space. For our first problem, let's find the distance from a point P1 to a plane that has the normal vector n and which contains the point P0. So let's define a few things. We'll say that the normal vector is ABC, and then P1 will be the point x1, y1, z1, and then P0 will be the point x0, y0, z0. Notice that the distance that we want is the magnitude of the projection of the vector b as drawn onto the normal vector n. Magnitude or absolute value. From trig, we see that this magnitude is the magnitude of b times the cosine of the angle between vector b and vector n. So the distance is going to be the magnitude of b, and then the cosine of theta is n dot b over the magnitude of n times the magnitude of b. These two magnitudes cancel. And then I'm going to put an absolute value around it because it's a positive quantity, which means that the distance is going to be the absolute value or magnitude of n dot b over the magnitude of n. Now, what is this vector b? Well, b is really the vector P0 to P1. So if I want to find the distance, I can do vector n, which we called ABC, dotted with my vector b, which is going to be the vector x1 minus x0, y1 minus y0, and then z1 minus z0. All divided by, I put it over here just for the sake of space, the magnitude of n, which gives us ax1 plus by1 plus cz1, and then minus ax0 minus by0 minus cz0, all over the magnitude of n, which is a squared plus b squared plus c squared, all square rooted. And you'll usually see this written as ax1 plus by1 plus cz1 plus d, all over the square root of a squared plus b squared plus c squared, where d, of course, is this part back here. So let's do a problem with that. Let's find the distance between parallel planes. 10x plus 2y minus 2z minus 5 equals 0, and 5x plus y minus z minus 1 equals 0. So what we need is a point in one of the planes, and we need the normal vector to either of the planes. It's going to be the same normal vector since the planes are parallel, or at least a multiple of the same normal vector. So I'm going to pick a point out of the second plane, and I'm just going to guess and check it. It looks like we have the point 1, negative 3, 1 is in this second plane. And then my normal vector to really either of the planes, is 10 to negative 2, which I could simplify, but I'm not going to here. And now let's look back up here. We can simply plug in here to get the distance that we want. So the distance is going to be the absolute value of 10 times x1, and then plus 2 times y1, and then minus 2 times z1, and plus d, which is negative 5, all over the square root of 10 squared plus 2 squared plus negative 2 quantity squared. And if we were to simplify this down, we get 3 over the square root of 108. And if you really, really want to keep going, but I'll let you do the work on this, that can simplify to root 3 over 6. Let's try a different type problem. Let's find the equation of the plane that goes through 1, negative 1, negative 1, which is parallel to the plane 5x minus y minus z equals 6. So since the plane I want is parallel to a given plane, they will have the same normal vectors. Or that is, the normal vector to the second plane, the given plane, will also be normal to the unknown plane. So the normal vector is 5, negative 1, negative 1. And then if you recall, we can write the equation of a plane as a times x minus, say, x1 or x naught, I'll call it x naught, plus b times y minus y naught, plus c times z minus z naught equals 0. Where the normal vector we'll define as ABC, and then our point will be x naught, y naught, z naught. And then we can simply plug in. We get 5 times x minus the x value, plus b, so negative 1, times y minus the y value, or y plus 1. And then plus z, so negative 1 times z minus z naught equals 0. And we get 5x minus 5 minus y minus 1 minus z minus 1 equals 0. Or 5x minus y minus z equals 7. Let's try a different type of equation. That is a different type of problem. Consider two planes, x plus 4y minus 3z equals 1, and negative 3x plus 6y plus 7z equals 0. Are these two planes parallel, perpendicular, or neither? So the easiest way to do something like this is not find the angle between the two planes, but to find the angle between the two normal vectors. So I'll call the first one n1, which is going to be the vector 1, 4, negative 3. And then the normal to the second vector, that is to the second plane, which I'll call n2, is the vector negative 3, 6, 7. And now let's do the dot product of these two vectors, which is going to give us negative 3 plus 24 minus 21, which equals 0. So we're not trying to find the actual angle, because if we did, we need to divide both of these pieces by the magnitude of our normal vectors. But since we see that the dot product is 0, This implies that the angle between the two vectors is 90 degrees, which means that our two planes are perpendicular to each other. Let's try one final problem, different from the others. But let's find the equation of the plane that is the same distance from the points 1, 0, negative 2, and 3, 4, 0. So my drawing is not going to be to scale at all, but just to kind of see what's happening. Suppose I had the point 3, 4, 0 up here, and the point 1, 0, negative 2 over here, and the plane is right there between them. One thing I definitely know is a point on the plane. Because I know a point on the plane must be exactly halfway between these two points here. And I made it perpendicular, but it doesn't have to necessarily be perpendicular. I just know the plane is exactly halfway between those 2 points, or at least that there is a point such that it is halfway between those two. So a point on the plane has to be the following: 2, 2, negative 1. I can guarantee this is a point on my plane. Now, because they are equal distance, and a distance is always perpendicular, I'm going to go back and put my perpendicular there. So I know that a normal vector to the plane must be the vector that runs between the 2 points. So the point 3 minus 1, 4 minus 0, and 0 minus negative 2. So a normal vector to the plane is 2, 4, 2, or I can simplify it down to 1, 2, 1. Well, now that I have a normal vector to the plane that I want, and a point on the plane, I can simply write my equation. So reminder, it's a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where this 1, 2, 1 is going to be our a, b, c. So I get 1 times x minus the x plus 2 times y minus the y, and then plus c times z minus the z. And writing this out, we get x plus 2y plus z. Now I'll go back and pick up the numbers. Then minus 2 minus 4 plus 1 equals 0. Which means the equation of the plane that we want is x plus 2y plus z equals 5.